This time we have a long list of recurrence relationships, and the question is, can we prove them? Obviously, it's a good idea to try and build on top of stuff that you have already done before. So as usual, pause the video to try just that. What have we shown before? Well, we have seen that if we take the derivative of the generating function with respect to t, that we can write down that jn minus 1 of x plus jn plus 1 of x, that's equal to 2n divided by x jnx. And we've also shown that if you take the derivative with respect to t, you get something that looks similar, the minus sign over here. And then finally on the right hand side, we have 2jn prime of x. So these are useful equations to keep in mind. Let's call the first equation 1, for example, and then the second equation 2, obviously. Now, if you stare at these equations for long enough, you will notice that if you add them, that then this second term over here will just disappear. So if you take these two equations, add them and divide by 2, what do you get? Well, you get that jn minus 1 of x is equal to n divided by x jn of x plus jn prime of x. And if we scroll back, that's exactly the first relationship that we needed to show. So that was not so bad, was it? And that also points the way towards solving the second task. Namely, this time we're going to subtract these two equations and divide by 2. Because then the first term will drop out, and then we can just write that jn plus 1 of x is equal to n over x jnx, and then we have a minus sign here. Good. So these were all just one-liners. Let's see now how we can show C and D. So these are derivatives involving the product of a power of x and then a Bessel function. So let's copy that again. We need to show something related to d dx of x to the power of n j n x. First thing we're going to do is whip out our chain rule. So then we take the derivative of the first factor. It becomes n x to the power of n minus 1, jn. And then moving on, plus x to the power of n j n prime. If we try and build on top of stuff we already know, so for example this equation over here, which looks awfully similar, the only difference is that over here we have a term jn prime multiplied by x to the power of n, whereas over here that x to the power of n is not present. So that suggests that we try and factor out this x to the power of n. So x to the power of n factored out gives us then n divided by x jn. So that works, because then if this x to the power of n, if we divide that by x, it indeed becomes x to the power of n minus 1. So that's good. And then finally we have jn prime. And if we identify the stuff between square brackets here, that's exactly this equation over there. So we can show that this is equal to x to the power of n j n minus 1. Let's just quickly double check. Indeed, this is what we needed to show. Finally, with negative powers of x, we need to show something related to x to the power of minus n jn. Proceeds in a very similar way. Again, first step is the chain rule, minus n x to the power of minus n minus 1 jn plus x minus n jn prime. Let's look for something that we can use. Obviously, this time it's going to be that expression over here. So again, you will notice if you just look at the coefficient of Jn prime, then we will be able to identify what we need to factor out. So if you compare that expression over here with this expression over there, then it becomes obvious that what you need to factor out is minus x to the power of minus n. Doing that, we get an n divided by x jn minus jn prime, which is indeed what we needed to show is equal to jn plus 1. So that we were able to show all of these recurrence relationships. And actually these final two relationships, it turns out that these are incredibly helpful once you try to solve integrals involving Bessel functions, and more specifically the product of a Bessel function and a power of x. But that's the subject for another exercise.